So we've solved our exponential equations, we've covered a lot of different examples, and now let's look at some logarithmic equations. So much like I was thinking about before, I needed to isolate the exponential expression, then deal with the logs. Same idea here, except for this time I'm going to have to isolate the logarithmic part. So if I do that, I'll do that by subtracting 4 from both sides. So I have log base 2 of x is equal to minus 3. So let's see. There's a couple ways to think about this next step. If I'm given the logarithmic form, one way you can think about it is I can switch it to its exponential form. That's to say, I have the base, which is 2. I go to the other side to get my exponent, which is 3. Well, minus 3. And then x. Oh, I've solved it. Again, you may actually have written this as x is equal to 1 over 2 to the third, or 2 to the third is just 8, so 1 over 8. And of course, what I will say, you're going to always want to go ahead and check these. So always check the logarithmic equations, log equations. And again, the reason is that our domain for a general logarithmic equation, if you think about its graph, it looked like this. So the domain here was 0 to infinity. So there are restrictions on what we can plug in. And when we solve, we may accidentally introduce another equation or another solution. So how do you check them? Again, just like you would always check, go ahead and take my initial expression, which was 4 plus log base 2, and we found it's the value of x is 2 to the negative 3, and we're asking, is that equal to 1? Well, 4 plus, remember this expression right here, the bases match, so they cancel with the log, gives you 4 plus a minus 3, which is definitely equal to 1, so this does check out. In other words, our solution set here is just going to be to the negative 3, or one of its equivalent forms. So we'll just put 1/8. So let's see what other flavor these problems come in. In example 6, we have two logarithms. And again, I kind of mentioned this in the last example, but recall that a function that is 1-to-1, a logarithm is an example of a 1-to-1 function, hence it has an inverse. So we have 1-to-1 that each y value there is a unique x value. So keeping that in mind, how many solutions does a logarithmic equation have? Well, it should have just one, of course, maybe none, depending on how your logarithms are set up here. You may not have one that satisfies both. But then we have compositions. So again, this is really more just to iterate the fact that you need to be checking your solutions. All right, so on to this equation. We have log base 3 of x minus 8, and we have log base 3 of x equals to 2. So I can't just switch to the exponential form because I have two logs. I can't take two logs and switch it into one exponent form, but this is where section 3.3 comes in. I could go ahead and combine these. This is plus, so I can use the product rule. The product rule just said, if I have plus, I could write them as one log, same base, but I have x minus 8 times the x equal to 2. Simplify this, you have log base 3 of x squared minus 8x equals to 2. And again, you could think about this in terms of switching it to an exponential form. And something else that you occasionally see is just, you know what, remember how let's just back up last section. We did like x squared equals 9. You go ahead and take the square root of both sides. So if I can do that with square roots, it feels like, you know what, I can just go ahead and use these as an exponent, 3. If we remember how I removed the base earlier, why can't I just put it back? So now if you think like this, if we're thinking about it, 3 is now my number, and then this line right here are exponents. Well, the reason I did that is so this canceled. So we have x squared minus 8x equals to 3 squared. Again, it's the same thing if you switch to its exponential form. You would have done 3 to the square is equal to this, so it all comes out the same way. course, this is now quadratic. I can easily solve x squared minus 8x, subtract 8 from both sides, or 9 from both sides. So minus 9 is equal to 0. Again, where do I get the 9 from? From right here, 3 squared is equal to 9. Slide down and make some room to finish solving this. Of course, I can factor this as x minus 9 and x plus 1 equals to 0. So x is equal to 9 and minus 1. And again, let's go ahead and check these to see which of these is the solution. So I want to go ahead and check it back in my original function, or my original equation. So the first thing I'll check is 9. Is log base 3 of 9 minus 8 plus log base 3, 9 equals to 2. Log base 3, simplifying here, you get 1 plus log base 3, well, 9 is just 3 squared. Is that equal to 2? Well, this cancels because anytime there's a 1 in there is 3 to the 0, so it's just 0. Plus 2, is that equal to 2? Yeah, so 9 is part of our solution. And now checking minus 1, well, log base 3 of minus 1 minus 8 plus log base 3 of minus 1, is that equal to 2? And really, we can't even go anywhere farther if we think about this. This is negative. This is negative. There's no way to deal with a negative input to a logarithm. It's just undefined. So this, again, you can't do anything with. So we can throw out negative 1. So our solution set here is just the single value of 9. And again, I will emphasize that, you know what, this you really need to check because there's a lot of things to consider when it comes to compositions and the product of logarithms with other functions, and there's a lot of different cases. So here's several different examples just dealing with logarithms. I encourage you especially to try A. I will go ahead and write the answers to these so you could check them with the notes posted on the course shell. But again, practice, take your time. If you have any questions, feel free to ask, and have a wonderful day.